Welcome, chemistry students. We're about to begin solution stoichiometry, but right before we get started, got a little joke here for you. Taking a look at what do you call a tooth in a glass of water? A 1 molar solution. Come on, that was pretty good here. Introducing solution stoichiometry to us as we solve stoichiometry calculations based on some aqueous solutions. This should look very familiar to you, our GMV setup where we have grams, moles, and volume, which needs to be measured in liters. And the new kind of concept here for us is the fact that we can use molarity, which is moles per liter, to convert from volume to moles of a substance. So as a quick example here, if you had like 15 liters of solution and you wanted to figure out of a solution at 2.0 molar, so the molarity is 2.0, you could basically figure out how many moles do you have present. And the way you would do that is obviously I'm starting here in my liters of solution and I'm trying to get to moles, so I can use molarity as a conversion factor. You take what you're given, 15 liters over 1. I'm going to bring down liters and I'm going to go to moles. And my molarity is 2.0 molar, which is really 2 moles per 1 liter. Right? That's what molarity is. So right here I can use it as a conversion factor. 2 moles per 1 liter. Liters cancel, 15 times 2, and we get 30 moles as your answer there for that problem. So let's put that to use here when we actually use a conversion and do a sample problem. So right here we're using solution stoichiometry to determine the mass of aluminum. So that is my mass is going to be grams unknown of aluminum. Need to react with 30 mils. And up here I'm just going to convert this to liters. So it's going to be 0.300 liters because I need to know to convert milliliters to liters every time. And it has a molar concentration of 2.50, capital M for molarity. And you always want to start with your given that is not a fraction. And since this is basically 2.5 moles per liter, and this is just liters, I'm going to start with my given, that is 3 liters. So I'm given 0.03 liters of H2SO4, my sulfuric acid, and I need to convert that to grams of aluminum. So if we go back to our map here real quick, on this problem I'm starting with 3 liters of my H2SO4 and I need to get to grams of my unknown. So I need to do a volume to mole conversion, and then I need to use my mole ratio, which we use a balanced chemical equation for, and then very easy, we've done probably 1,000,000 times, a mole to gram conversion. So those are my basic steps that I'm going to follow to solve this problem. And when I go from volume to moles in a solution stoichiometry, we use molarity as my conversion factor. So I have liters of H2SO4. I'm going to bring down liters of H2SO4, and I'm going to moles of H2SO4. We always want to get to moles. The moles to liter is the molarity. It's 2.5 moles per 1 liter. Liters cancel. I'm now in moles. Set up my next train track. I can bring down moles of H2SO4, and I am going to moles of my unknown aluminum on top. This is moles over moles is my mole ratio. It is a 2 to 3 ratio because I have a nice balanced chemical equation here. so it's a 2 to 3 ratio. I'm now in moles of aluminum. My last step is to do moles to grams. So moles of aluminum to grams of aluminum. In 1 mole, I'm going to find the molar mass of aluminum on my handy-dandy periodic table, which is going to be 26.98. And now all I need to do is type it in my calculator and solve the problem. Typing this in and calculating, we end up with 1.35 grams of aluminum as the mass needed to react with that much sulfuric acid. Let's do one more example problem here for solution stoichiometry so we really have a good grasp and understanding of this. And we're on this problem right here. What mass of hydrogen gas would be produced? So I'm trying to find hydrogen gas. So over here, this is my grams unknown from 20 milliliters of sulfuric acid. I'm going to convert my milliliters to liters. And remember, there's 1,000 mils in a liter. So I just moved the decimal 1, 2, 3 spots. So it's 0.02 liters. And again, the concentration stays the same, 2.5 molar, which remember, it's moles per liter. I just like to rewrite molar as moles per liter because we know to use it as a conversion factor if it's a fraction. Our whole number, that's just a regular unit, can't use that as a conversion factor because there's not a top and bottom. And then it's telling me that I have excess aluminum. Just put that there as a note. Again, I'm going to start with my 0.02 liters of sulfuric acid over 1. Bring down liters of sulfuric acid, and I'm going to moles of sulfuric acid, H2SO4. This is where I can use the molarity as a conversion factor. It's 2.5 moles per 1 liter. That gets rid of my H2SO4. Next step, bring down moles of H2SO4, and I'm going to moles of H2, my unknown. The ratio is a 3 to 3 ratio, so it actually ends up being just 1, which is nice. And then my last step is to do moles of H2 to grams of H2. And 1 mole, hydrogen is 1.01, but I have 2 of them, so that makes it 2.02 as its molar mass on the periodic table. And I'm going to simply type that in my calculator and solve the problem. Solving this out, we get 0.101 grams of H2 produced. Last problem for the solution stoichiometry example here is if we react 3.5 grams of aluminum. So I'm going to write this down here, 3.5 grams of aluminum and 45 milliliters with the 2.5 molar solution of sulfuric acid. So 45 milliliters is going to be 0.045 liters. And again, it's 2.5 moles per liter for the molarity of the sulfuric acid, its concentration. How many milliliters of aluminum sulfate, so this is ml, unknown, milliliters of aluminum sulfate solution would you get? And it's telling you the aluminum sulfate concentration is 1.5 moles per liter, right? Molarity, I rewrite my molarity always as moles per liter because that's really what it is. So this problem, I'm going to start with my 3.5 grams of aluminum because that's the only one that has one thing here. And I'm trying to go from grams of aluminum to milliliters of aluminum. So let's set up our equation or our train tracks, 3.5 grams of aluminum over 1. And I know this is going to be a long one, so I'm just going to write it out. I need to bring down grams of aluminum, and I'm going grams to moles of aluminum. Right? In 1 mole, there are 26.98 grams. I just look on my periodic table to get the molar mass. Grams cancel. Now I can do moles of aluminum to moles of my unknown, which is my Al2SO4. Correct? This is my mole ratio here. I can see that it's a 1:2 ratio. Cancels my moles. Bring down moles of Al2SO4, and I'm going to milliliters of Al2SO4. And really up here, this is 1.5 moles per liter, so really it's liters if I use 1.5 moles to 1 liter, because there's a 1 there, and then I'll just convert my answer back to milliliters in the end. So we can go ahead and solve through here, type this in our calculator. And then calculating this out, we ended up with 43.2 milliliters of Al2SO4. You can see here I converted the milliliters, the liters here that we had. This was liters. I converted it to milliliters by multiplying by 1,000. Now, that's how many milliliters we could get if we use all 3.5 grams of the aluminum. Well, what about the 0.045 liters of the sulfuric acid? Maybe we end up using all of this up first, and we actually can't produce that many milliliters of the aluminum sulfate, or vice versa. It's kind of a limiting reactant problem. We've done limiting reactant problems before. So I'm going to set this one up here. I'll use the blue for this one. We're going to do the exact same steps to solve and see which one is the smaller answer and what actually limits how much I can actually produce. So again, I'm going to start with the 0.045 liters of H2SO4 over 1. I'm going to bring down liters of H2SO4, and I'm going to moles of H2SO4. In 2.5 moles, there's 1 liter. That's the molarity, or the concentration, of my sulfuric acid. So it's 2.5 moles per 1 liter. Allows me to cancel liters. I can now bring down moles of H2SO4, and I'm going to moles of my aluminum sulfate, Al2SO4 3. Checking my mole ratio here, it is actually a 1:3 ratio. 1:3. Cancel my moles. I'm now going to bring down my moles of the aluminum sulfate, Al2SO4 3. Actually, see a mistake I made up here with these, in that I have a 3 that I should have on those. Not a big mistake, but that might be, some of you might have caught that and saw that in the formula, so add those in. But I'm in moles of Al2SO4 3 to the liters of Al2SO4 3. And again, this is moles over liters. I can flip my molarity, and it's really just 1 liter and 1.5 moles. So 1 liter is 1.5 moles. Now everything cancels, and I'm going to get an answer in liters that I will then convert back to milliliters. And then calculating this out, we end up with 0.025 liters times 1,000 gives me 25.0 milliliters. That is actually my final answer, because I really could not produce 43 milliliters. I would run out of sulfuric acid before I would get to the 43 milliliters. Using up all of my sulfuric acid, I get 25 milliliters of the aluminum sulfate. So the limiting reactant in this problem is sulfuric acid. So that's your LR, your limiting reactant. And the amount produced here is actually limited to the 25 milliliters. And that's solution